So let's start today's lecture of this modern physics course. Last time we spoke about the quantization of charge, light and energy. For that we studied the discovery and the measurement of the elementary charge and its mass, and the quantization of light with the description, the correct interpretation of the blackbody radiation, when it is said that the oscillators in a radiating material emit light at a frequency, at some frequency, which is the frequency of their oscillation, and the energy of packets of light, which are called photons, is proportional to this frequency through the coefficient h, which is the Planck constant. And we also saw the photoelectric effect, where the light is quantized. Really, the light consists, or can be described as consisting of packets of energy, which are, each packet is proportional to the frequency of the light. So the energy of the photon is proportional to the frequency of the light. And we also saw the Compton effect, which is described as a collision between two particles. One particle of light, which is the photon, and one electron of material, metallic material, and both particles are described through their energy, and it's a relativistic energy, and their momentum. And so we saw the expression for the momentum of light, the linear momentum, which is not proportional to the mass of the photon, because the photon, having a speed equal to c, has no mass. Okay. So today we will see the structure of the atom. So it's called the nuclear atom. We don't have yet a clear idea of how the atoms are constructed, they are built. Okay. The scientists at the time, they knew that there were atoms. Okay, there are a lot of works done in chemical sciences, in physics also. But so what is known is that the atoms are neutral, electrically neutral. Let me see here. I will speak here of the atomic spectra, but okay, first. So the atoms are electrically neutral, but it is known that they have electrons. So there are some positive charges and some negative charges, and no idea at all about how these charges are distributed inside the atom. We have an idea of the dimensions of the atom. Okay, atoms are typically have dimensions. Okay, of the order of 10 to the minus meters, which is 10 to the minus meters. It is called an angstrom, and so these are typical dimensions of atoms. Okay, so before looking in more detail what may be the structure of these atoms, we are going to speak a little about the atomic spectrum. Okay, so there are a lot, okay, of experiments done with light, okay, to try to understand what is light, and how it can be described, and how it can be manipulated. And one of the experiments, what can be done, you have here a source of radiation, you pass this source through a slit, okay, and you have some dispersive element here. This is a prism, and so this dispersive element will spatially separate the spectral components of the light, meaning that if you put a screen or you record on a photographic plate what is observed here, you will have some relationship between the position here of the light incident on the screen and its wavelength. Okay, so you can detect the spectrum of the light. So if it is, for example, a completely white light, or let's say black body radiation, okay, we have seen that you can vary, okay, the angle, okay, and if you study, actually, here you observe the angle, okay, of the incidence of this light, and the light emitted by a black body has a continuous spectrum, okay. It means that you have the presence of all the components of the spectrum, okay. Just a minute. And so it is a continuum, so it has some shape, okay, it has a maximum at some wavelength, but there are no wavelengths missing in the spectrum, okay. And so when you do this kind of experiment and you record on the screen here, you are doing some spectroscopy, okay, you are measuring the spectrum of some light source, okay. So what can be done with that? Instead of here, if you have a source of wavelength, okay, and so you pass them through a slit and a prism which will disperse the light, so you will spectrally separate the two wavelengths or the three wavelengths or whatever the number of wavelengths are present in this source, okay. And so what they do, they pass some light. For example, this source of wavelengths, it can be an atomic gas. For example, you have some lamp, okay, and so these atoms inside the bulb, they are excited through electronic discharge, for example, and so when they are excited, you observe, okay, you can observe the emission of light, and so you have emission of light by some excited medium, okay, and you observe with this spectrometer, you observe the spectral composition of this light. And what you observe is very interesting, because depending on the gas you put here, okay, inside the lamp, you have, for example, for hydrogen, okay, you will observe not a continuum as you can observe with a black body radiation, but lines, okay. So this is in emission, this is brilliant, okay. This is the impression of your photographic plate, for example, and so you see a number of lines, and they are called lines because of that, okay. And if you calibrate your plate here, your screen, you know exactly, okay, as a function of angle, you know exactly what the wavelength is, okay. So here you have decreasing wavelength, increasing frequency, and if you do it again and again, you will always observe the same spectrum. And if you do it for, this is again for hydrogen, you can do it for other gases. Here for sodium, okay, sodium, you know, still today it's used for illumination, okay, in the cities. And so it's yellow light, and it has a very known couple here of wavelength, one at 589.5 and the other 588.9 nanometers, okay? And these are two, this is the D1 and D2 of sodium. I won't speak of it now, but you can see these two lines here on the plate. Depending on the specific element, you separate them or not. Here they are not really resolved, okay? And so you have here the spectrum of sodium, okay, which is here at small wavelength. This is visible. And you have spectrum, you have emission spectrum. So when you have emission spectrum, you have only some lines, bright lines on your photographic plate. And if you study absorption spectrum, you will have some, if you illuminate what is the difference between the absorption and the emission spectrum here, if you want to measure the emission spectrum, so you put some continuous source of light, a white source, a source of white light, and you put some sample of your gas, and so you will detect what is transmitted by your sample, and so you will observe the absorption spectrum, because the wavelengths which are absorbed, they won't be transmitted, they will be absorbed, okay? So what you observe in an absorption spectrum, you have the continuum spectrum of your light, okay, exciting light, okay, and here you have some lines missing, okay. This line was absorbed, this one was absorbed, etc. Okay, and so this is very strange and very reproducible. So reproducible that, for example, in 1885, Johann Balmer he studied this, and he tried to put an empirical formula to describe what he was observing for hydrogen, and so he called it lambda. This is the wavelength, and m is some quantum number. We now call it quantum number. It's simply an integer, okay? And for the line he was studying, he find this relationship between the wavelength, okay, and some number. So if you change the number, you put here, for example, n equal to 3, okay, so you will have lambda 3 equal to some value, okay, etc., etc. So later, Rydberg and Ritz, they generalized, okay, this relationship to any number, okay, n, and so you have here a dependence on two integers, okay, m and n, and so you have your wavelength depending on these two numbers, and they thought it was it followed 1 over lambda, okay, depending on these two numbers, has this dependency on these numbers, m and n, okay, and here obviously the wavelength is positive, so you have here m, which is the smaller number of the two, and you have here some constant he adjusted, okay, for this equation have a good agreement with the experimental spectra. And so he found this value, and this is called the Rydberg constant for hydrogen. Okay, so it's 1.096708, okay, 10 to the 7 per meter, okay. And so this is a phenomenological, okay, relationship between the wavelength and some numbers, okay, and obviously they don't have any idea of what these numbers could be, okay. So actually we have using this general Rydberg-Ritz equation, okay? So you can vary n and m as long as m is smaller than n. So let's see here 3 very famous lines, okay? They have the name of the scientist who described them. First, Lyman. Here it was Balmer, okay? So the Lyman series is for m equal to 1, okay? So if I substitute here m by 1, I will have this, the first wavelength, okay, is lambda 1, 2, okay? M equal 1, n equal 2. And if you calculate here with the value of the Rydberg constant, and so you will find that this wavelength is at 121.6 nanometers, okay? It is not here on this spectrum, okay? So what is the color of this light? This is ultraviolet, okay? I can put it here. This is UV, okay? Very small wavelength. And you can do it for, okay, 1 over lambda 1, okay, m equal to 1. So after 2, n equal to 2, I will put 3, 1 over lambda 1, 4, blah, 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 blah. And so as you are increasing, okay, the value of this second number, n, okay, you are decreasing the wavelength. And so the smallest one is the limit, okay, of the series, and it is called, for this series, m equal to 1 is the limit series, okay? And so infinite. So instead of n here, you put the infinite, okay? So you will have 0. And so you will have this value of the limit for the Lyman series is 91.2 nanometers, okay? So you can do that for the Balmer, which is called, so this one is essentially UV, okay? This is UV. And so if you go to the Balmer series, m equal to 2, so you have n, which can be varied between 3 and infinity, okay? And so the first one, 1 over lambda 2, 3, okay? You have here 2 squared, here 3 squared. So this is proportional to the Rydberg constant, and you find that this wavelength is red, okay? 656 is red, okay? Is it red? Yes, I think. And so you can calculate also for lambda 2, 4, okay? Lambda 2, 5. And so the limit of the series is for n equal to infinity here. And so you find that the limit of this Balmer series is 364.7 nanometers, which is UV. Okay. So this is essentially, the Balmer series is essentially in the visible and UV, close UV, okay? Range of the electromagnetic spectrum. And the third very known series is the Paschen series for m equal to 3, okay? So you vary n from 4 to infinity. And so if you calculate the smallest one, okay, the highest, the biggest one, the biggest wavelength for the smallest quantum number here, for the smallest value of n, is 1.88 micrometers. So this is infrared, okay? And so you can calculate also lambda 3.5, lambda 3.6, etc. Okay, and so you can calculate until the limit of the series, which is at 820.6 nanometers, and this is still This is still infrared, okay, but very close infrared, okay. So the patient series is in the infrared, okay. So the question next, okay, this is very interesting, okay. We have a phenomenological relationship, this Rydberg-Ritz equation, but we don't have any idea of where it comes from, okay? So certainly it comes from the way the charges are organized inside the atom. So first we have a model for the atom, okay? So I can write here, it is known that the atom is electrically neutral. There are the same number of charges, positive and negative charges. It contains electrons, okay, which are the negative charges, which are much lighter than the atom, okay. For example, you know that in an hydrogen atom, okay, so you will have an electron, okay, if you ionize this atom, and you will have, okay, one elementary charge, and here you have the proton, okay, this is essentially a proton, and so you know that the mass of the proton is of the order of 2,000 times, okay, 1,800 and something, okay, heavier than the electron, okay. So this is what is known about this structure, and what is known also is that the hydrogen atom spectra, they obey the Rydberg-Ritz formula. So how can we arrange, okay, these charges inside the atom so that they are, okay, the atom is electrically neutral. This is easy, okay, you put the same number of protons, let's say, than electrons, okay, and they have to obey, okay, this Rydberg-Ritz formula. So we have first the Thomson's model, okay, where you have an homogeneous distribution of the negative charges in some fluid, okay, positively charged. The problem with that, okay, so it has a lot of advantages, but the problem with that is that Thomson couldn't make this model obey the Rydberg-Ritz formula, okay? You can have some oscillations of the charges. The problem is that when these charges oscillate, they will lose energy because they radiate energy, and so they are losing energy, and in a continuous way, and so you don't observe any spectral lines, okay? And so who found a model which had all these characteristics, okay, is Rutherford with his students, and for that he used alpha particles. Alpha particles is a kind of particle which is emitted by the decay of radioactive atoms, okay, and so through some experiments, okay, Rutherford made, actually he was interested in the radioactivity, okay, so he found that the ratio of the charge on the mass, okay, of this particle, this alpha particle, was half the ratio of the charge on mass of the proton, okay. P is for proton. Essentially, this is hydrogen nucleus, okay. And so these particles, these alpha particles, they are helium atoms twice ionized, okay. You ionize, they have normally 2 electrons, and so you ionize it twice, and so you take out the 2 electrons, and so you have an alpha particle. What is nice with this particle that it is quite heavy. It has a charge which is interacting. Okay, it's easier to study charged particles because you can manipulate them with electric fields and things like that. And so he did a series of experiments. So he had some radioactive source here inside some shielded box, okay, because radioactivity is not very good for the health, and also because he wanted to have a beam of these alpha particles, and so he has to let these particles get out of the box through a small aperture, okay, so that he has something like a beam that he can direct at essentially a foil. I don't think this is gold here, but it is a metallic foil, okay? And so what he detects, okay, in this experiment, okay, you have some target here, projectile which are alpha particles, and he has some a scintillation screen. So this is when the particles, these are particles, alpha particles, they are scattered by the foil. This is a thin foil, okay, metallic foil. And so as a function of theta, you measure the number of, or the fraction of the incident particles, which will put this screen to scintillate, okay? And so you can observe this. You have a microscope and you observe and you do some very precise measurement, okay? Each time a particle, an alpha particle, is incident of the screen, so the screen will emit some signal, okay, light signal that you can observe, okay? And so why, this is the Rutherford experiment. Why is it so important? Because it allows, still today we have big, okay, scattering experiment. We have collision rings, okay, very expensive and very big collision rings where you put some particle you want to study. They are the projectiles or they are on the target. And so you have a lot of detectors, okay, and you have some model, okay, for the scattering process, the collision process between, for example, here the alpha particles and your target. And so you try to have a model of the interaction between these two the particles, okay, which obey, okay, which interprets well your experimental measurements. So if the Thomson's model were right, what we have is that each time a particle, an alpha particle, collides with an atom, okay, if this is the kind of atoms in the foil, okay, it would be, okay, so this is He++, so this is a positive charge, so it will be scattered by the charges inside the atom, okay, but anything you do, you will have a very small scattering angle because this is a very soft interaction because the atom is big, okay, it's small but it's quite big in terms of the size of these particles. And so if the charge is really homogeneous on all this R, okay, the radius here of the order of 10 to the minus 10 meters, okay, you can show that the density, okay, of charges is very small and you won't have a very large scattering angle, okay. But what Rutherford and his students observed was that a lot of particles were indeed scattered at very small angles, but a significant number of them also was scattered in angles higher, bigger than 90 degrees. So you have here the direction, okay, so 90 degrees is here, okay. So here you put your scintillation screen, okay, and this is a very big angle, okay. It should be a few degrees, okay, at most. And you observe here at 90 degrees, and you also observed at angles bigger, okay, than 90 degrees, and it's a significant number. It's not something you can neglect, okay? So you cannot explain this result with the Thomson model. So what Rutherford said, okay, his model, he said that the charges, they are not distributed, the positive charges are not distributed in homogeneously in the atom, okay, but they are all concentrated in what he calls the nucleus, okay, and the radius of this nucleus is much smaller, okay, than the radius of the atom, which is on the order of 10 to the minus 10 meters, okay, and so we will see that it is actually on the order of 10 to the minus 15 meters, okay, so it's 5 orders of magnitude smaller in that. So you have a very big in space, okay, a very discontinuous, okay, charge density, okay. There is no charge, and suddenly in this very small volume you have all the charge, okay, in a very, very small volume. So it should give way to a result very different from what is expected with this model. So let's see. First, we will see what is called the distance of closest approach, okay? And this is this model, okay? You have the alpha particle, and you have an infinite mass here for your nucleus, okay? So you consider that your nucleus is much heavier than your alpha particle, and so you have some, you will see, we will use here some reference frame, okay? And you put, actually here, it will be 2-dimension. You have okay, let's say X, Y, Z, and you put your nucleus here, okay? Z is the atomic number, okay, and E is the elementary charge, okay? So you have a very big mass here, and you say that, okay, this is an approximation. This nucleus won't have its momentum changed by the collision with the alpha particle, and you will have scattering of the alpha particles. Scattering is simply is a collision, okay? This is a collision between the two of them, and so you have a lot of way of colliding, okay? So after that I will show you a non-frontal, this is a frontal collision, and this is the strongest collision you will have, because if you draw a line between the two particles, okay, the alpha particle and the nucleus, okay, of your target, your foil, your metallic foil, okay, so the particle has some energy, kinetic energy, half its mass times its velocity square, and so you will have conservation of the energy, and so here you consider that U equal to 0, okay, you have no potential energy between the particle, the alpha particle, and the nucleus, and here you have some turning point, okay, turning point, and what happens at the turning point? The kinetic energy is 0, okay, the velocity is getting smaller and smaller and smaller, it is 0 here, and it increases again on with the opposite sign, okay, for this distance here, okay. So this is the closest approach. This is the the point, okay, where the alpha particle will come closer to the nucleus, okay? And what happens here, you have U, you have K, okay? Initial, okay? And here you have K final, K0, and here you can calculate, okay? You can calculate it. This is the Coulomb, okay? Coulomb potential. And so you know the expression, okay? So this is what we will call K, okay? Because, okay, K or 1 over 4 pi epsilon 0, okay? And so this is the atomic number of the nucleus, the foil. This is the atomic number of the particle. Here this is an alpha particle, so Z equal to 2, okay? And so you calculate, okay, you solve this equation on D, okay, this closest approach, and you see that it depends on the kinetic energy, obviously, of the alpha particles, okay? And so this is the Coulomb, this is for Coulomb interaction, purely Coulomb interaction, okay? And so if the collision is non-frontal, okay, so what happens is you have here your nucleus, okay, nucleus, you have your alpha particle, okay, this is your alpha particle, it has some velocity v initially, okay, so far away from the nucleus, okay, the energy is 100% kinetic energy, and as it approaches the nucleus, you have potential energy, and you have energy conservation, okay, during the collision, during the scattering process. And so you can show that this is a central force, okay, and so it can be shown that we have conservation of energy and also of the angular momentum, because this is a central force. So this is a very important result of the classical mechanics, okay, that in the case of central forces, you have conservation of the angular momentum as well, okay. I won't go into the details, okay, of this description here of the collision, but this is a very basic description. So you have conservation of energy, you have conservation of the angular momentum. So you can show that the scattering angle here, okay, not actually we will call theta, but theta is the scattering angle. But first we have the impact parameter, which is the distance, okay? You have the line here where you have your nucleus, and you have a parallel line, which is the line of approach of your alpha particle. And so the distance between these two lines is called the impact parameters, okay? What we saw just before was for B equal to 0, okay? When you have a frontal collision, you have B equal to 0, okay? If it's not frontal, okay, B different is 0 if it's non-frontal collision, okay? And so, what is important here, so you have the force at any position here. You have this central force, which is the Coulomb force, okay? And this is a Coulomb force between the projectile and the scattering nucleus, okay? And we can deduce from these two laws of conservation, okay? We can deduce a relationship between this angle of deflection, okay, this scattering angle theta, and the impact parameters, okay? And so this is this one, okay? I won't demonstrate this relation. Okay, so you have for an alpha particle approaching on the nucleus with an impact parameter B, okay? So the angle, the scattering angle will be theta, and the relationship between the two is this one. Q alpha is 2e, Q, this is z, okay, e, and this is the mass of the alpha particle, and this is the velocity of the alpha particle. It has this velocity here initially, and when it gets rid of the repulsion, actually, okay, with the interaction with the nucleus, it also has the same velocity, which is logical because here you have no potential energy, you have no potential energy. So the kinetic energy, the initial and final kinetic energy are the same, okay? What is important here, okay? I will give you some homework, okay, to apply some of these relations. But to show you, we don't need to go into the details, okay, of these collisions. What we have is, you have two alpha particles. One is alpha 1, alpha 2. Alpha 1 has an impact parameter B1, alpha 2 has an impact parameter B2, which is bigger than B1. And so as it is farther from the nucleus, okay, so it will be scattered at a smaller angle, okay? You imagine that at the limit of no deflection, okay, theta will be 0, okay? So you have the incident. So if you have a particle approaching the nucleus very far away, okay, with a very big impact parameters, so there will be no detection, okay? So this is theta equal to 0, okay? And here, the bigger the impact parameter, the smaller, okay, the scattering angle, okay? So we already found this relationship here, okay, applying the laws of conservation. Here I showed you, actually this is only this part of the, okay, of the graph, okay, because we have here theta will be between 0 and pi over theta will be between 0 and pi, okay? So because it is this cylindrical symmetry, so this doesn't apply here. But what you see is that as you increase the angle, theta, this quantity cotangent of theta over 2, okay, which is here, it decreases, okay? So you increase the angle, you decreases, or better, you increase the impact parameter, you decrease the scattering, okay, the scattering angle, okay? So we can make some, obviously you don't choose, okay, which particle and which impact parameter you will have. You have some very large beam, okay, and so each particle in the beam, okay, will have some impact parameter B, okay, and of this B depends the scattering angle, okay. So you have the intensity I naught, okay, this is the number of particles per unit time, per unit surface, okay, and these are the incident particles, okay, and each of these particles has some impact parameters, okay. And if you want to calculate the number of particles which are scattered at an angle bigger than theta I, for example, so you know that as there is a very you have a direct relationship between theta and B, so it has to be for impact parameter B smaller than Pi, okay, with Bi and theta I related through this relation, okay. So the number is this one. What is the number? Here we can see it. you have all the particles. See here, for example, from B2, impact parameter B2, what is the area, okay, of this? You have all the particles which are, okay, inside, okay, this cross-section here, they will be deflected at an angle which is higher than the value for this one, okay? So if you have, this is the angle, okay, this is theta, the deflection angle, and all the particles inside, okay, this cross section, they will have angles which are higher, bigger, okay? So this is the area, pi bi square, okay, times the number of particles per unit time per unit, okay, per unit area. And so this is for one nucleus and I naught particles, okay? And so we have this number, okay? But now we know that all these alpha particles, they will not be scattered by the same nucleus, okay? There will be a few of them, okay? In the foil, there will be a lot of them. So it will depend on the density of the material. It will depend on the thickness of the material of the foil, okay? And so the number, okay, if you have, so one particle, one nucleus, one particle, I naught particles, okay, we just saw it. And now, okay, this is a very simple explanation. You have the area A of the beam, okay, and so it describes some, it has some, it will be scattered by some volume, okay, in the foil. So you have the thickness of the foil, which is T, okay, and which will be important here is the area of the beam, okay. Of course, on the part of the foil which is outside the beam won't scatter alpha particle, okay. So you can call in N the number of nuclei inside a small volume per volume unit, VU, okay. So you can show this is the density, okay. So this is kilogram per cubic meters, okay, times this unit, okay. So this is 1 cubic meter if you want, okay, and this is the mass of the of the nucleus, okay. And so we can write the mass of this nucleus, which is the molar mass divided by the Avogadro number, okay. And so we write it. So we have some relationship between, okay, the number of nuclei inside the volume, okay, the scattering volume, okay, and data of the material, okay, material. So you have the density, you have the molar mass also, okay. And so, doing some very simple algebra, you have the total number of alpha particles scattered at an angle larger than theta I, okay. This will be the number of which we already for one nucleus it was this one, and so times the number of nuclei in the scattering volume, which is T times the area, okay, the area times the number of nuclei per unit volume, okay. And so if you want to calculate the fraction, okay, of atoms, okay, scattered at an angle theta larger than theta I, so you have this one, you divide by the total number, okay, of alpha incident on the foil, okay. So you have these relations, and so this is it, okay, for the Rutherford. So this is a model, and so now what you have to do is looking for the interpretation of the experimental result with this analysis. Okay. So oh, I didn't write it. Oh, something is missing here. I'm sorry. Because what is important here is that all the dependence, okay? Yes, one slide is missing. You have the fraction, so you measure this fraction, okay, of alpha particles scattered at an angle higher, larger than some given scattering angle, okay? And you have here a relationship between this quantity you measure and this one, I remember you, okay? So this is, you can know it, you know, okay, you can calculate for the foil, you control it, okay? And this P, okay, there is a relationship between this P, okay, and this theta. So, and there is a relationship also with the kinetic energy. So all of this has been shown, okay, experimentally shown to be coherent, okay, with this model. So you have as a function, okay, I won't write as a function, okay, it's F theta with the kinetic energy of the incident alpha particles with the thickness, okay, so with T, okay, which is the thickness of the foil, with what else? With the material, okay, material. So what is important in this material? This is Z, okay. This is the molar mass and the density, okay. And okay. So we have almost finished, okay, with this. So it has been shown to work, okay. So if this is a model which described very well, okay, the experiments, the scattering experiments, and so as long as it works, we can say it is a good model, okay. What one thing, okay, there is some approximation which has been done here. We are seeing in this model that the interaction between the nucleus and the alpha particle, it is Colombian, okay, and that the atom, okay, here actually, the particle, the alpha particle, won't go won't penetrate actually inside the nucleus, okay? And so actually, if you increase the kinetic energy, okay, and so you see if you increase the kinetic energy, you will have, so you will increase this, you will decrease, okay, this distance of closest approach, okay. It won't be zero, okay, because it won't work, okay, with the Colombian interaction. When you have a very strong kinetic energy, very high, so the particle can penetrate, okay, the nucleus, but the forces at play here will not be Colombian ones, okay, there will be nuclear forces, and so you will have a different behavior. So this is very good because you do some experiments, and as long as it obeys, okay, the Colombian interaction, so you say it is. You can write these expressions, and when it started, so for example, you increase the energy, and at some moment, okay, you increase, so you are decreasing D, okay, calculated through this expression, and there is a moment where increasing the kinetic energy, you will not have anymore the agreement between your model and the experiment, okay, so the experiment will be different. It will show different results. It is because you are starting to have the effect of other forces. And so it is understood to be for this smaller distance where the Coulomb interaction still works, okay, that you will call this will be here. This will be the radius of your nucleus, okay? So you have a direct relationship, okay? So the maximum energy you have here will correspond to the minimum D, and so you will say that K max, okay, max in the Coulombian regime, okay, will be proportional to 1 over R of the nucleus, okay? And so you measure, okay, you do a study varying this K max, and so you can have an idea of the nucleus radius, okay? So this is an example of the Tipler, I think, the book, okay? The radius of the gold nucleus has been measured by other techniques, okay, to be 6.6 femtometers, okay? Femtometers, 1 femtometer is 10 to the minus 15 meters, okay? What kinetic energy alpha particles would Rutherford have needed, okay? So that for 180, okay, scattering 180 degrees. So this is the frontal, okay, the frontal collision. The alpha particle would just reach the nuclear surface before reversing direction, okay? So this is this relation here. So you put here the numbers, you know the value of epsilon. This is K, 1 over 4 pi epsilon 0, okay? You have here the atomic number of the gold, okay, atom. You have here the atomic number, of the alpha particle, which we call Z. This is the charge, the meteoric charge, okay, squared. And here you have this dimension, okay, measured. And so you calculate, and this is it's quite a high energy. You remember the relationship between Joule and electron volts? 1 electron volts equal to 1.6 10 to the minus 19 Joule, sorry. Okay, and knowing that his Rutherford source of alpha particle was radioactivity, okay, so he didn't have access to this kind of high energies. He did it actually with aluminum, okay, and so he had energies available, okay, a little larger than this one, so he could measure, okay, the nucleus of the aluminum atom as being of the order of 10 to the minus 15 meters. And now we know that it is 3.6 femtometers. Okay? So I will stop here now.